Namaskaram everyone. Dear students, welcome for another day of webinars. Today, the first session is going to be Mathematics 1A, continuation of the chapter which was started, Mathematical Induction by Sri Raja Prabhu Sir, PGT Mathematics from TSMS Gavicharla, Warangal Rural District. So, children, I hope you all remember, and I'm sure you will remember and you have practiced the questions which were given based on mathematical induction. And you also should be eagerly waiting to do few more problems based on the same concept, based on the same principle of mathematical induction. I just want to recollect, there will be 3 steps. Isn't it? The first step, when we take n is equal to 1 and we prove it, then we assume, we go for induction hypothesis, where n is taken as k and we assume that the statement is true for n is equal to k, and then final and third step is to prove the statement to be true for n is equal to k plus 1. Isn't it? Are you ready? Here we go. I welcome Sri Raja Prabhu Sir, PGT Mathematics, to take over the session. Over to you, sir.
Thank you, madam. Thank you very much. So, a pleasant good morning to one and all. Thank you, madam. It's my pleasure to continue the second session on the principle of mathematical induction. So, good morning, students. Students, I hope you all are ready to attend my session. So, before I come to the session, already just now, madam also reviewed. Actually, the statement, the principle of mathematical induction here is, already you know, just let me recall that once again. If P of n is a mathematical statement, and to prove that statement is true, we are going to verify at 3 steps. Okay, already you know that. What are they? Students, are you able to answer? Yes, the first step is just verifying that n is equal to 1. I mean, by substituting the place of n 1. Okay, and the second step is, yes, what is it, children? Second step, it is nothing but the inductive hypothesis. At this step, we will be assuming that the statement is true for a certain value of k, where k is also any natural number which is greater than or equal to 1. And the third step, you know that is the major part of our problem. That is nothing but inductive step. So that is proving that the statement P of n is true for n is equal to k plus 1. That means substitute in the place of k plus 1 and verifying that. Means we have to prove P of k plus 1 is true. Okay, when any statement is true at these 3 steps, then we can confirm that, or we can conclude that the statement will be true for any natural number. Yes, children, already we have learned all these things in the previous session. Okay, now it is the time to continue for few more problems. Children, please get ready and try to be alert always and try to understand each and every step. So already you know this mathematical induction is one of the methods of the proofs by the process of verification. Okay, children, so I'm coming to for the next problem. Okay, please continue that. is giving you here one problem. In the last session, I have covered few problems, whatever was possible. Now I'm trying to cover some other type of problems again. Okay, of course the method will be same. There is no much difference between any two problems here in the exercise given to you. Okay, now coming to this new problem, let us identify what is it given here is. Yes, children, the problem given here is use mathematical induction to prove the statement 2 plus 3 into 2 plus 4 into 2 square plus next term you can guess that will be 5 into 2 cube and so on up to n terms, which is equal to n into 2 to the power n, where for every n belongs to n. That is a given problem here. Okay, children, what is our common procedure? For our convenience, in the very beginning step, we will be assuming that the statement is some p of n as it is in terms of n. Okay, so let p of n is equal to the given statement, that is 2 plus 3 into 2 plus 4 into 2 square plus and so on up to n terms, which is equal to n into 2 to the power n, which is to be proved. Okay, now identify, children, here. In this problem, there are two sequences. There are two sequences known as two different types of progressions. You notice, children, here I have something is displayed on the screen now. In the given problem, you can notice here that the first term is 2, the second term is 3 into 2, whereas the third term is 4 into 2 square and so on. Here, the first term can be considered 2 into 1, which is not necessary to be written there, but you can understand. Here, it is consisting of two progressions. What are they here? One is 2, 3, 4, the first terms, 2, 3, 4, 5, 6, and so on like this. Let's identify this. These terms are in AP, whereas the first term is 2, second term is 3, third term is 4, and so on. You can notice, or you can identify the nth term very clearly without using any formula. Identify, children, here. In the first term there is 2. That means just one more than 1. Second term is 3, that is 2 more than, sorry, 1 more than 2. Third term is 4, that is 1 more than 3, and so on like this. The nth term also will be 1 more than n. Therefore, the nth term will be automatically n plus 1. Okay, these all are in terms of AP. These are the terms of AP. Okay, in the same way, whereas the second second sequence is starting from 1. Okay, identify here. Second is starting from 1. Second term is 2. Third term is 2 square. Fourth term is 2 cube, and so on like this. The nth term will be, also you can guess here. First term is 1, nothing but that can be written as 2 power 0. Second term is 2, nothing but 2 power 1. Third term is 2 square, nothing but 2 to the power 2. In the same way, the nth term here, you can identify one thing, that in the power will be 1 less than the number of term. Therefore, the nth term will be just 1 less than 2 to the power 1 less than n. That means the nth term will be 2 to the power n minus 1. So there will be no confusion at all. Children, you please understand, the nth term of the second sequence here is 2 to the power n minus 1, which is a GP. All these terms are in geometric progression. So all these terms already you know in your 10th standard, so that I feel you will be feeling very convenient to understand this. Therefore, now the nth term of the series given here is nth term of the series given, nth term of the first AP, that is n plus 1, into the nth term of the GP, that is 2 to the power n minus 1. Therefore, the product of these two terms will be, nothing but n plus 1 and 2 to the power n minus 1 to the nth term of the given series. Okay, that is the first thing that you need to identify. Now we are going to prove this. So how to prove means using only the principle of mathematical induction. For that, already you know the step 1. What is step 1? We will be verifying whether it is correct for n is equal to 1 or not. It means we are proving that p of 1 is true or not. Okay, for that what we do? The common procedure, just substitute in the place of n1 in both LHS and RHS. So automatically you can, that will be the procedure here. So what is LHS here? Nothing but the nth term. That nth term is n plus 1 into 2 to the power n minus 1. Now substituting the place of n at 1 and simplifying here. Okay, then we get here n nothing but 1. That is 1 plus 1 into 2 to the power 1 minus 1. 1 plus 1 is 2, whereas 2 to the power 1 minus 1 is 2 power 0, nothing but 1. 2 into 1 is 2. Okay, a very simple simplification, very simple step. Now let's go for the RHS also. In that, RHS means the formula to be proved here is n into 2 to the power of n. In this also, substituting n is equal to 1. So 1 into 2 to the power 1, which is equal to 1 into 2, which is equal to 2. So here it is very clear that LHS and RHS, both of them are equal to 2. They are equal. Means here it is verified for n is equal to 1. That means the statement is true for n is equal to 1. That means P of 1 is true. Okay, now this is the first step. What is the second step? That is the induction hypothesis. Nothing but we have to assume that the statement is true for some positive integral value of k, that is nothing but n is equal to k, where k is also a natural number or positive integer which is greater than or equal to 1. Okay, for that, then as we are assuming that p of k is true, then p of k will be, that is 2 plus 3 into 2 plus 4 into 2 square plus 5 into 2 cube and so on, up to the nth term, sorry, up to the kth term here, that is k plus 1 into 2 to the power k minus 1, which will be equal to k into 2 to the power k. Okay, now let us assume that is some equation 1 for our convenience, which we are going to use in further steps of this proof. Okay, this is the induction hypothesis, that is step 2. Now let's come to step 3. What is step 3? That is the main part of our proof, that we have to prove it is true for n is equal to k plus 1. Means up to the k plus 1th term also it will be true, that we are going to verify. For that, what to do? First, we have to find the k plus 1th term. So you know that the nth term is n plus 1 into 2 to the power n minus 1. Therefore, the kth term is, already we have written that in the second step only, that kth term is indicated by tk, which is equal to k plus 1 into 2 to the power k minus 1. Now to get the k plus 1th term, substitute in the place of k or in the place of n k plus 1. Then what it becomes? Tk plus 1 is equal to, that is in the place of k there is k plus 1 plus 1 as it is, into 2 to the power, into 2 to the power k plus 1 minus 1. Just here in this step, in the place of k plus 1 is substituted, and just simplify that. What is that? Tk plus 1 will be is equal to k plus 1 plus 1 is 2, and 2 to the power of k plus 1 minus 1 becomes, gets cancelled, then 2 to the power of k. Now that is the k plus 1th term. So as you know that after finding the k plus 1th term, to get p of k plus 1, we have to add that k plus 1th term, that is k plus 2 into 2 to the power of k on both sides of that equation 1. Then we will get p of k plus 1. So here to get p of k plus 1, adding k plus 1th term, that is k plus 2 into 2 to the power of k on both sides of the equation 1. Equation is very clear, it is just before you. Okay, after adding the k plus 1th term, what we get here, that will be p of k plus 1 is equal to 2 plus 3 into 2 plus 4 into 2 square plus and so on, up to the k term is k plus 1 into 2 power k minus 1, and up to the k plus 1th term is k plus 2 into 2 to the power of k, which is equal to k plus 2k plus that added term k plus 2 into 2 to the power of k. Now this is p of k plus 1, which we are going to prove now. Okay, how to prove? Just simplify this right hand side part and try to express that in the given format. Okay, what is the right hand side part? K into 2 to the power of k plus k plus 2 into 2 to the power of k. Okay, children, you identify what to do now. Yes, it is very clear. There are two terms. Among those two terms, one term 2 power k is common. So taking the 2 power k as common. Okay, then what will get? Take out 2 power k common, then the remaining term in the first term here is k, and the remaining part in the second term is k plus 2. So it is now 2 power k into k plus 2. Okay, now small simplification, that k plus k becomes 2k. So the next step is 2 power k into 2k plus 2, and again there is other common term, that is 2 among those two within the bracket. So take out 2 also common, then it becomes 2 power k into 2 into k plus 1. Children, I hope you are able to understand that easy simplification part. So try to concentrate. Okay, now what is this? What we can do in the next step? Here 2 power k into 2, just like bases are same, so you can add the powers. Then what it becomes? 2 to the power 2 to the power k plus 1 into k plus 1. Okay, that k plus 1 is written before, then k plus 1 into 2 to the power k plus 1. Identify what is given. The given sequence in RHS part of the given sequence is, it was n into 2 to the power n. Students, you identify here is very clear. In the place of n we got now k plus 1, so that itself is to be proved. Therefore now we can assume, or we can conclude that the statement is true for n is equal to k plus 1. Now the statement is true for n is equal to 1, and according to our induction hypothesis it is also true for n is equal to k, and according to the third step it is true for n is equal to k plus 1. As it is following all the three steps, as it is true in all the three cases, then we can conclude that by the principle of mathematical induction, according to all these three steps from 1 2 and 3, we can say that the statement is true for any value of n. So therefore we can say that the given statement is correct, hence it is proved. Yes children, this is about the proof of the first problem what I considered today. So I hope you are exactly following me. Try to follow that. Okay children, then also already I instructed you in the last session that try to note down immediately on this part. So you please follow that even today also in this session also. Okay, so can I think y'all are ready to face the next problem. Okay children, I'm coming for that. Let's see what is it. The same heading, using mathematical induction, prove that. Here is a little different problem, but which will be very easy. One small suggestion, one small submission, students, don't afraid of seeing the problem anywhere. So just try to follow the same steps and try to involve by knowing your, by applying your known concept, then automatically the problem will take you to get the solution. Okay, so what is the problem given here is 1 cube by 1 plus 1 cube plus 2 cube by 1 plus 3 plus 1 cube plus 2 cube plus 3 cube divided by 1 plus 3 plus 5 and so on up to n terms, which is equal to n by 24 into 2n square plus 9n plus 13. Okay, now this is the problem given. Here also the nth term is not given. We have to find the nth term. So how to find it? Just by going through the oral observation of the other given terms, then automatically you will get an idea to get the nth term of this problem also. See children, what is there? The first term is 1 cube by 1. Okay, and the second term is 1 cube plus 2 cube by 1 plus 3. Okay children, you might have noticed that there is, all the terms are in fraction form. There is a numerator and denominator in all the terms. So look at the terms. First numerator of the all the terms. First term is 1 cube. Second term is 1 cube plus 2 cube. Third term is 1 cube plus 2 cube plus 3 cube, and so on. Then what will be fourth term? Will be 1 cube plus 2 cube plus 3 cube plus up to 4 cube. In the same way, suppose some 10th term will be 1 cube plus 2 cube plus 3 cube plus 4 cube 5 plus 5 cube and so on up to the 10 cube, etc. In the same way, what is the nth term? Nth term will be 1 cube plus 2 cube plus 3 cube and so on up to n cube. Nothing but that will be the sum of the cubes of first n natural numbers. Okay, that is about the numerator. And what is the denominator? You see children, here first term, denominator of the first term is 1. Denominator of the second term is 1 plus 3. Denominator of the third term is 1 plus 3 plus 5. Okay, here I am explaining orally to observe. Children, you concentrate on the problem and also attend my explanation here. In the denominator, there are odd numbers. In the first term, there is only one odd number. In the second term, there are two odd numbers. In the third term, there are first three odd numbers. Automatically, in the fourth term, there will be first four odd numbers. In the same way, in 10th term, there will be first 10 odd numbers. And in nth term, there will be first n odd numbers. Okay, see what is that? Already you know all these. So, okay, before we come to the problem, you know, the very first step, we have to consider P of n as the given statement. Okay, that statement is this. And next, here I'm trying to write the nth term of this series given. Already I explained to you orally just now. See what is there? The numerator of the nth term is 1 cube plus 2 cube plus 3 cube and so on up to n cube. That is nothing but sigma n cube, or simply you can say the sum of the cubes of first n natural numbers. Whereas the denominator is 1 plus 3 plus 5 plus and so on up to the nth odd number. Okay, already in the previous session we have seen this problem. It is also one of the arithmetic progression with the common difference 2 and the starting term or the initial term is 1. So the nth term will be, you can calculate children by following the formula of nth term of arithmetic progression, that is Tn is equal to a plus n minus 1 into d, you will get 2n minus 1. It is very simple concept already known to you. I have written it directly here. That is the nth term of the denominator here is 2n minus 1. Therefore, the nth term of the series, I mean nth term of the problem or nth term of the statement is given as 1 cube plus 2 cube plus 3 cube and so on up to n cube whole divided by 1 plus 3 plus 5 plus and so on like this up to the nth term, that is 2n minus 1. Okay, children, now you have some specific formulae for them. You can recall, you have to remember them. What are they? 1 cube plus 2 cube plus 3 cube and so on up to n cube. That is sum of the cubes of first natural numbers, which is equal to, yes, children, can you guess what is it? That is n square into n plus 1 whole square divided by 4, which is known to you already at 10th standard. So you please remember it. You have to recall all the basics which you have learned in the previous sessions. In the same way, the sum of the first n odd natural numbers, already we have proved it in the last session, that will be n square. Okay, therefore, now the simplified step of the nth term of the series or nth term of the given statement is, that is numerator. For the numerator, it is n square into n plus 1 whole square by 4 whole divided by, for the denominator, that is n square. Okay, now after small simplification, we will get here n square into n plus 1 whole square by 4n square, whereas n square gets cancelled. What is remained then? N plus 1 whole square by 4. You see, children, the nth term of this sequence is very simple now. It is in simplified terms, which is equal to only just n plus 1 whole square by 4. Therefore, now the sequence can be written as, the series can be written as, what is it? So, I mean, P of n will be up to nth term. Okay, now you know here we have to prove it is true for all the values of n. For that, okay, this is the first step. The first step is we have to prove that it is true for n is equal to 1, means substituting n is equal to 1 in the left hand side part and also right hand part. Okay, what is LHS? Nothing but nth term of the series. Just now we proved it, just now we have written it, we have calculated it, that is n plus 1 whole square by 4. Now substitute n is equal to 1 in this, what you get? 1 plus 1 whole square by 4. 1 plus 1 is 2, 2 square by 4, which is equal to 4 by 4, nothing but 1. So LHS value, we got 1. And what is RHS? The given part I see, that is n by 24 into 2n square plus 9n plus 13. In the here also, in the place of n, we have to substitute 1 and simplify. Okay, n by 24, that is 1 by 24 into 2n square, 2 into 1 square plus 9 into 1 plus 13. Very easy simplification. Here 1 by 24 is ISTs, and 2 into 1 square is 2 plus 9 into 1 is 9 plus 13, which is equal to 1 by 24 into 2 plus 9 is 11, 11 plus 13 is 24. So 24 by 24 is also 1. Okay, now we have got here LHS is equal to RHS, both of them are equal to 1. Therefore, we can conclude that it is verified for n is equal to 1. Then what is the next step? The second step, that is the induction hypothesis. The induction hypothesis is, we have to assume. What to assume? Assume that it is also true for n is equal to k, where k is any natural number and greater than or equal to 1. Okay, let us see. Then I'm writing the statement for P of k. So P of k will be same statement, 1 cube by 1 plus 1 cube plus 2 cube by 1 plus 3 plus 1 cube plus 2 cube plus 3 cube divided by 1 plus 3 plus 5 and so on up to the kth term. Now the kth term is k plus 1 whole square by 4. The nth term is n plus 1 whole square by 4. Kth term will be k plus 1 whole square by 4. Automatically that will be is equal to k by 24 into 2k square plus 9k plus 13. Okay, for our convenience, let us consider that is equation 1. Okay, children, now let us go to the third step. The third step is that is nothing but we have to prove the statement is true for n is equal to k plus 1. Okay, means we also required to find the k plus 1th term by using the nth term or kth term. Okay, what is the nth term that we know? It is n plus 1 whole square by 4. So automatically the kth term will be, already we have written that in the previous step, that is k plus 1 whole square by 4. And next, our important step to get k plus 1th term means substituting the place of n or k, that's k plus 1. So tk plus 1 is equal to k plus 1 plus 1 whole square whole divided by 4, which is also equal to k plus 2 whole square by 4. Okay, children, now this is the k plus 1th term. So what is the next step to continue the problem? We have to get p of k plus 1. That means we are writing the statement up to the k plus 1th term. Nothing but add the tk plus 1, which is equal to k plus 2 whole square by 4 on both sides of that equation 1. Okay, adding that. So then what we get? We will get here p of k plus 1. Okay, that is 1 cube by 1 plus 1 cube plus 2 cube by 1 plus 3, 1 cube plus 2 cube plus 3 cube by 1 plus 3 plus 5 and so on. Up to the k plus 1th term is k plus 2 whole square by 4, which is equal to, here you know, up to the kth term this is, that is k by 24 into 2k square plus 9k plus 13, and up to the k plus 1th term means also plus k plus 2 whole square by 4 will be. Now we have to prove this right hand side part, uh, that it is true for n is equal to k plus 1. Already you know, already I told you in the previous session that we can guess the answer before we prove it. So what guessing that we require? Only thing we need to get in the place of n k plus 1. See children, up to the kth term it is k by 24 into 2k square plus 9k plus 13. So in the final step we have to get in the place of k plus 1 means here k plus 1 by 24 into 2 into k plus 1 whole square plus 9 into k plus 1 plus 13 should come. So just simplify this total RHS part and get that answer. So what we do? Just you do LCM and simplify here. Okay, it's very clear. There are two terms, two numbers in the denominator, that is 24 and 4. As 24 is a multiple of 4 or 4 is a factor of 24. LCM of both of them is 24 only. So 24 by 24 for the first step, for the first term I'm writing now, that is 24 only, and just multiply the numerator directly and write here. Okay, what is that here? K into 2k square is 2k cube plus k into 9k is 9k square and plus k into 13 is 13k. Okay, and for the next term here, the second term, the denominator is 4. Now 24 by 4 is 6. 6 into this numerator, that is k plus 2 whole square. So 6 into k plus 2 whole square is k square plus 4k plus 4 according to a plus b whole square formula. Okay, children, this I hope this is very clear to you. Okay, now the next step. Next step is also simplifying the just numerator. Okay, here the denominator is common. Let it be 1 by 24 as the quotient. Next, what is numerator? Here is 2k cube I is 9k square I is 13k I is, and now 6 into k square is 6k square. 6 into 4k is 24k and 6 into 4 is 24. Okay, now this we got. Now what to do here? According to our final view, means expecting the final answer, we need to follow the steps here. So what we can, already I told you just now, in the place of n there should be n plus 1. So for that, what I'm doing here in the next step, identify children, this is the very important step. Of course here it is, these all are added simply. 1 by 24 into 2k cube is this 9k square plus 6k square is 15k square and 13k plus 24k is 37k, and this 24 is ISTs. Okay, here this is a very very important step that you have to concentrate much more here. We have to split these four terms according to our requirement. So what requirement we need, you need to guess that by expecting our final answer. Okay children, now let's see. Just trying to factorize the numerator here. Okay, how to factorize this numerator, very important thing. Children, I hope you learnt different methods at your 10th standard to factorize any second degree, third degree, fourth degree polynomials. Okay, here it is a third degree polynomial in terms of k. So how to factorize third degree polynomial? According to your 10th standard, here there is a specific method known as harness method, or you can follow even ordinary method also, ordinary division method also. But I want to follow, I want to continue this with harness method. Just I am factorizing this third degree polynomial, which is in terms of k. Okay, how to factorize it? Now you see children, there are different uh, different steps to follow the factorization, different methods to follow the factorization of any third degree or fourth degree. Just like the factor theorem, mm, or the remainder theorem, basing on that. Okay, here I think this is not the time to specifically to explain that, so I'm coming to this very directly. You please follow that. Here you follow the coefficients of various terms in this given polynomial is, in the polynomial here, coefficient of k cube is 2, coefficient of k square is 15, coefficient of k is 37, and the constant term is 24. You follow children here. Suppose if sum of all these coefficients is 0, then compulsorily k minus 1 will be a factor according to the factor theorem that you have studied in 10th standard. Here, but sum of the coefficients is not 0. Then the other alternate method here, you also check sum of the alternate coefficients. Children, you follow 2 plus 37 is 39, whereas 15 plus 24 is also 39. Nothing but here the sum of the alternate coefficients of various terms of this polynomial are becoming equal. Therefore, we can say that that k plus 1 will be a factor of this polynomial. Nothing but according to the factor theorem, if you substitute in the place of k minus 1 in this case, the value of the polynomial becomes 0. Therefore, k is equal to minus 1 will be one of the zero of this polynomial, or we can say k plus 1 will be a factor of this polynomial, that you have to identify orally. This is very much essential to know. So after the identification of one of the factors, that is k plus 1 is factor of this, then you go to the next step. Okay, already you know the harness method. Okay, here there is a small inconvenience, children, you please try to understand. Okay, here I have already listed out all the coefficients. What are they? 2, 15, 37, 24. And the left side there is minus 1. That is for this like divisor. Why I should consider, why I have considered minus 1 means here k plus 1 is a factor, just now we concluded. When k plus 1 is a factor, then minus 1 will be a 0 of that polynomial. So I'm trying to divide this by minus 1. The student, those who do not know this procedure, you also can follow the ordinary division method. Means you divide this total polynomial, that 2k cube plus 15k square plus 37k plus 24 by k plus 1. Then also you will get the quotient here. Then you can go for the next steps for the factorization. Okay, here I'm following this. Okay, here actually I should give you the number step by step, but some inconvenience the PPT part. So try to understand, children. Okay, first here under 2 you will be writing 0. Then here you have to add 2 and 0. Then 2 plus 0 is equal to 2, which will be written in the first column. And then this minus 1 and minus 1 and this 2 will be multiplied. Minus 1 and 2 are multiplied. Then 2, the product of these two, 2 into minus 1 is minus 2. That should be carried here. It should be written under 15. Then again add these two. 15 minus 2 is 13. Then again multiply 13 by minus 1. 13 into minus 1 is minus 13. Write that next product under 37 under the next coefficient. Then 37 minus 13 is 24. Again 24 into minus 1, which is equal to minus 24, right under the next term. Now 24 minus 24, which is equal to 0. Okay, so now these are the coefficient that we got, that is 2, 30, 24, 0. Now what is there here, what we can understand from that? Children, you see here, these terms 2, 13, 24 will be the coefficients of the quotient, which is formed by dividing this numerator, this polynomial by k plus 1. Okay, therefore, now these are the coefficients of the quotient. So this quotient will be now, quotient will be, what is the quotient? That is indicated by some q of k, as this in terms of k. It is now 2k square plus 13k plus 24, that is written here. So once again, try to understand, students, by dividing this polynomial by k plus 1, we will get this as a quotient, and this part which is indicated here, that is nothing but remainder. It will be remainder, that remainder here is 0. Therefore now this polynomial 2k plus 15k square plus 37k plus 24 can be written as, that polynomial can be written as the product of these two factors. What are they? One is k plus 1. The other factor is the quotient what we got now, that is 2k square plus 13k plus 24. Okay, here if you have any difficulty to understand this step, students, you please refer the 10th class polynomial chapter once again, so that you can understand. Okay, I hope, children, you will be following me. Okay, now we have to continue this. So this is the expression which to be proved now. For that, still I'm trying to split this into our required part. Okay, this k plus 1 is ice teas. K plus 1 is ice teas. And 2k square is also ice teas. 13k is written in two parts. That is 4k plus 9k. 13k can be written as 4k plus 9k. Why to write only like this? Why not some 5k plus 8k or 3k plus 10k, etc.? It is according to our requirement, according to the solution that what we are expecting to prove it. It should be splitted only like that. And whereas this 24, again, this 24 also can be written in three parts, that is 2 plus 9 plus 13, etc. Okay, now let us see what is happening in the next step. Okay, k plus 1 is ISTs. Now here just the terms are rearranged. What is that? 2k square plus 4k ISTs, and this 2 is written here, and 9k plus 9 plus 13 remained ISTs. Okay, children, here this 13 you can expect, you can guess from the first question itself, I mean first problem itself. In the problem there is 13, so you write that separately. Now these three terms, from the first three terms, it is very clear that 2 is in common, whereas the next two terms 9 is in common. So taking 2 here and 9 here common, then we get here, that is k plus 1 into 2 into k square plus 2k plus 1 plus 9 into k plus 1 plus 13. Okay, also very simple step here. What is this part? That is k square plus 2k plus 1. This is in some a plus b whole square from nothing but a square plus 2 plus b square, which can be written as a plus b whole square, nothing but in the place of a there is k, and the place of there is 1. In the place of b there is 1. So the next step will be k plus 1 into 2 into that is k plus 1 whole square plus 9 into k plus 1 plus 13. So now you can compare this with our given problem. The RHS of the given statement is n into 2n square plus 9n plus 13 is there. Yes, children, you I think already have noticed it. We have got now in the place of n k plus 1, which is to be proved. Means we can say that the statement is true for n is equal to k plus 1, or you can say p of k plus 1 is proved. Okay, the same step is carried here. Therefore, now it indicates, or we can understand from this step, that p of k plus 1 is true. Means it is verified for n is equal to k plus 1 also. So by this, for this statement or for this problem, it is verified at three steps. Verified for n is equal to k, By the induction hypothesis, assumed that it is true for n is equal to k, and from step 3, it's also proved that it is true for n is equal to k plus 1. Therefore, now we can say that from steps 1, 2, and 3, by the principle of mathematical induction, you can say that the statement is true for any value of n. Means it's always true for all the natural numbers. The statement will be always true. So hence it is proved. Therefore, the given statement is correct. Okay, children, here in this problem seem to be some steps are little lengthy while simplifying, but in practice it becomes very easy. So you know that practice makes man perfect. Therefore, practice twice or thrice or any number of times until you get perfection. Okay, children, you please follow that. Now, this is the second problem. What I proved now. Now, let's go for another problem. So same title, that is use mathematical induction to prove the statement. Okay, what statement is given here? Yes, children, the question is on the screen. Let once have a glance at it. What is that? A plus AR plus AR square plus and so on up to n terms, which is equal to A into R to the power n minus 1 whole divided by R minus 1, where R is not equal to 1, and whereas every for all n belongs to n, nothing but small n is any natural number. Okay, what is it? Can you respond, students? Yes, respond yourself. That it is the general form of a geometric progression, and as there is plus in between all the terms, it indicates that the sum of n terms of a geometric progression. Students, I think you don't have the formula for sum of n terms of a geometric progression in 10th standard, at the 10th standard. Okay, but anyway, this is the formula, the right hand side formula, that's A into R to the power n minus 1 divided by R minus 1 is the formula to find sum of n terms of a geometric progression, where A is the first term and R is the common ratio, as you know, and n, you know, number of terms. Okay, here clearly it is indicated that R is not equal to 1. If R is equal to 1, then this formula is not applicable. Also, you notice that why this formula is not applicable if R is equal to 1. Once you see, when you substitute in the place of R1 in the both numerator and denominator, you will get 1 minus 1, 0 by 0. 0 by 0 is an indeterminate term which does not exist. I mean, the value of 0 by 0 is indeterminate. There is no value for that. Division by 0 does not exist. Therefore, specifically, R is not equal to 1. It is mentioned here. Suppose if you substitute R is equal to 1 in the given progression, then it may become AP. In general, in every geometric progression, the common ratio should not be 1. Okay, when we are finding sum of n terms, then automatically it becomes arithmetic progression. You can follow the concept of AP only to find the solution. Okay, that is a different matter. But now here our problem actually here is we are going to prove this by verifying. Okay, what to do? For the convenience, we have to consider that it is some P of n. The given statement is P of n. So P of n is equal to A plus AR square plus and so on up to n terms, which is equal to A into R to the power of n minus 1 by R minus 1. Okay, here nth term is not mentioned. So we have to get the nth term. Let us identify, just guess like the previous problems. R, you know, nth term of a geometric progression. What is it, children? Yes, it is there on the screen. That is A into R to the power n minus 1. Or you can, even though you do not know that formula, according to the previous sessions, you can understand, you can identify directly like previous problems. A is common in all the terms, and power of R is 0 in the first term, power of R is 1 in the second term, power of R is 2 in the third term, and so on. Therefore, the power of R in the nth term will be 1 less than n. That will be n minus 1. Means the nth term of the sequence here given is A into R to the power n minus 1, which is very important to identify. Okay, after writing that, then let us go for proving this. So we need to prove that the statement P of n is true for all natural numbers. For that, let us come to step 1. You know, step 1 is verifying for whether it is true for n equal to 1 or not. Okay, I'm verifying now by substituting the place of n1. Okay, what is the left hand side? I mean nth term, that is a r to the power n minus 1. In the place of n, 1 is substituted. Then a into r to the power of 1 minus 1, that is 0, nothing but a r to the power of 0. Something to the power 0 is always 1. Therefore, that is a into 1 is a. So we have got a in the left hand side. Now what is RHS? I mean that formula, a into r to the power n minus 1 by n minus 1. Here also substituting in the place of n1. Then we get a into r to the power 1 minus 1. That is nothing but r minus 1 by r minus 1 gets cancelled. Then the remainder is also only a. Remainder is only a. So it is also very clear LHS is equal to RHS. Means it is verified for n is equal to 1. That means P of 1 is true. Okay, the first step is finished. Then let's come to the induction hypothesis. That is step 2. So assume that the statement is true for n is equal to k, where k belongs to n and k is greater than or equal to 1. Therefore, P of k is equal to now up to the kth term. Up to the kth term, that will be a plus ar plus ar square plus and so on. The kth term will be a into r to the power k minus 1, which will be equal to a into r to the power k minus 1 divided by r minus 1. Okay. So this is the induction hypothesis. Consider that is equation 1. Now, what is the next step? That is third step, known as inductive step, that we have to prove it is true for n is equal to k plus 1. Means P of k plus 1 is true. For that, let us find the k plus 1th term now. You know nth term, a into r to the power n minus 1. Whereas the kth term is a into r to the power of k minus 1. Then automatically the k plus 1th term means in the place of n r k substitute k plus 1. So it is t k plus 1 is equal to a into r to the power k plus 1 minus 1, which is equal to a r to the power k. A plus 1 minus 1 gets cancelled. Yes, children, now this is the k plus 1th term. Now let us try to write the statement up to the k plus 1th term. So what to do for that? Adding that k plus 1th term, that is tk plus 1. That is a into r to the power of k on both sides of that equation 1. Okay. Now here we get P of k plus 1 is equal to a plus ar square plus and so on. Up to the kth term is a into r to the power of k minus 1 plus the k plus 1th term is a r to the power k, which is equal to up to the kth term the sum is a into r to the power of k minus 1 by r minus 1. As it is up to the k plus 1th term, the sum up to the k plus 1th term is plus a r to the power k. Okay, now we have to prove this. What to do? Very ordinary simplification here also. Okay, this is RHS which is carried here again. Now let's see. As it is in fractional form, again we have to do LCM. LCM of the denominators here is only r minus 1. So the first term r minus 1 by r minus 1 is 1. 1 into the numerator is IST. That is a into r power k minus 1. Okay, plus here this denominator into, I mean this is r minus 1 into this term. That is r minus 1 into ar to the power k. Okay, children, now by multiplying that, see what we got. Here very simple under simplification. Yes, what is done here, children, are you able to understand? Yes, there are two terms in the numerator. Among those two terms, okay, what is common here? A is in common. Yes, children, just you identify that A is common. Take out A common, then we get the remaining part in the first term is r power k minus 1. The remaining part in the second term is, that is r power k into r minus 1. Here, children, there is a small direct step. There is no direct step at all, but you can understand. Here is, these are multiplied. R power k into r becomes r power k plus 1, which is written here. Okay, and then plus into minus is minus, and r power k into minus 1 is minus r to the power of k. That's all. Now see, children, here r power k minus r power k plus r power k can be cancelled. Plus r power k minus r power k. It is very clear step. You please notice. And then the next step after the cancellation will be a into this positive term is written first, that is plus r to the power of k. R to the power of k plus 1 is here, and this minus 1 is here. Okay, children, and divided by r minus 1 is I stage. Yes, can you guess now what we got and what we have to get? Yes, we got what we need to get. That is the given question, RHS part of the given problem or given statement is a into r to the power n minus 1 divided by r minus 1. Here we got now in the place of n k plus 1, that itself is our proof to be proved. That means it is verified for n is equal to k plus 1. Therefore, p of k plus 1 is true. Okay, children, now this is the third step. So, what is our conclusion now? As it is verified at three steps, from steps 1, 2, and 3 by the principle of mathematical induction, it is true for any value of k, for any natural value. I mean, for all the natural numbers, etc. Therefore, the statement is true. Okay, so now we can say that the statement is true for for any value of n. Therefore, the proof of the sum of n terms of a geometric progression is a into r to the power of n minus 1 divided by r minus 1. Okay, children, now this is the problem based on geometric progression. Okay, let me come to the next problem. Okay, I want to cover some other type of problem which will be very simple. That too by using the principle of mathematical induction. Children, let us see. Yes, a small problem is given here. That is 1 square plus 2 square plus 3 square and so on up to n square is always greater than n cube by 3. Yes, children, try to understand that question first, the problem first. What is given? The left part here is sum of the squares of first 10 natural numbers is greater than, the right part is n cube by 3. I mean, suppose if you consider, suppose first term, 1 square is less than 1 cube by 3. If you substitute first two terms, means 1 square plus 2 square will be compulsorily greater than 2 cube by 3. If you consider first three terms, 1 square plus 2 square plus 2 will be compulsorily greater than, that is 3 cube by 3, sorry, 2, 3 cube by 3, etc. Okay, how to prove that using mathematical induction? Let us follow the steps here. This is a very simple problem which can be closed within 3-4 minutes. So for your convenience, you can consider that as P of n. And next, we need to prove it is true for all the values of n. Okay, for that, step 1. What is step 1? Just verifying whether it is true for n is equal to 1 or not. Okay, n is equal to 1 nothing but verifying up to the first term. First term itself is 1 square is greater than. Right side part in the place of n, you substitute n is equal to 1. Okay, what we got? 1 cube by 3. 1 cube by 3 is also 1 by 3. So you know that 1 is greater than 1 by 3. Yes, children, is it right? Is 1 greater than 1 by 3 or not? Yes, that is a simple concept. 1 is always greater than 1 by 3 means it is verified for n is equal to 1. By substituting the place of n, we have got that it is true. Okay. Now coming to the next, that is second step. What is the second step? Induction hypothesis. That is assumption. So you assume that P of n is true for n is equal to k, where k can be any natural number and which will be greater than or equal to 1. Then write the statement up to the kth term. So it will be P of k is equal to now 1 square plus 2 square plus 3 square and so on up to k square is greater than k cube by 3. Now consider this as inequation 1. You identify, children, it is not an equation. It is not an equation. It is an inequation because there is inequality symbol greater than symbol. So okay, consider that as inequation 1 now, which we are going to use in further steps. Okay, then let's go for step 3. What is step 3? We need to prove that the statement is true for n is equal to k plus 1. That is P of k plus 1 is true. Okay, means write the statement up to the k plus 1th term. You know the nth term is n square. Therefore, the kth term will be automatically k square. And the k plus 1th term will be k plus 1 whole square. Okay, now verify up to the k plus 1th term means adding that k plus 1 whole square on both sides of that inequation 1. Okay, children. So we get here now, that is P of k plus 1 is equal to 1 square plus 2 square plus 3 square plus and so on up to k square plus k plus 1 whole square, which also should be greater than k cube by 3 plus k plus 1 whole square. Now just we verify or we check whether it is correct or not. Okay. So it is now the same thing is carried here. The right part is k cube by 3 plus k plus 1 whole square we have got. Also do simplification, means by doing LCM, as in fraction form. LCM of both terms here is 3 only. So 3 by 3, 1 into k cube is k cube, whereas the remaining part here 3 into this numerator, that is 3 into k plus 1 whole square. Very easy simplification. Let us see now. K cube plus 3 into k plus 1 whole square is, according to just simple formula, plus v whole square, that will be k square plus 2k plus 1 whole divided by 3. Now children, again just simplifying this by opening the bracket. Okay, what do we got? 3 into k square 3k square plus 3 into 2k 6k plus 3 into 1 is 3 whole divided by 3 is this. Now also let's see what to do here. We have to express that according to the given term. I mean, in the given question, in the right hand side there is n cube by 3. We have to get now in the place of n k plus 1, means we have to get only k plus 1 whole cube by 3. That itself is enough. Okay, see now this term here, this 3k k cube plus 3k square is as it is. Now the 6k is written in two parts, 3k plus 3k according to our requirement is. Children, you try to understand and notice that. And 3 is written as 1 plus 2. Okay, the numerator is split into some other terms according to our requirement. Okay, now the next step. What is here, children? These first four terms. Okay, I think I need not explain much more clearly. These are in the form of some a cube plus 3a square b plus 3ab square plus b cube, where a is equal to k and b is equal to 1 according to a plus b whole cube. Nothing but k plus 1 whole cube plus 3k plus 2 is I t's and divided by 3 is also I t's. Now let's see. The same step is carried here in the next. I have written this in two parts by separating the terms of the numerator. It is written in two terms. See children, what is here? The numerator is k plus 1 whole cube by 3 plus 3k plus 2 by 3. It is split into two parts. Okay. Now what you can understand in this? Let's see. If you are able to understand this, that itself is mostly enough. What is this? For example, you know that 10 is greater than 7. Is it right, children? 10 is greater than 7. In the left side there is 10, in the right side there is 7. Now from the 7 I want to remove some term. Suppose I want to remove 3. Then 7 minus 3 is 4. Then after removing, the difference is also lesser than 10 or not? I mean 10 is greater than 4. What is this 4? That is 7 minus 3. Means from even the LHS is greater than RHS. From the RHS, if you remove something, then compulsorily the LHS will be greater than, compulsorily greater than, much more greater than the remaining part of RHS. So here the same thing is written, children. You try to understand that here RHS is this much actually. Sorry, RHS is this much. There are two terms in that. And from these two terms, here I remove this. Also make a note of it. This removed term must be positive. Yes, as k is a natural number, 3k plus 2 by 3 also will be positive part. So positive part is removed. When positive part is removed, then this LHS part will be compulsorily much more greater than this k plus 1 whole cube by 3. Therefore, we can conclude this now. This LHS, that is P of the total LHS part, that is 1 cube, 1 square plus 2 square plus and so on up to k plus 1 whole square will be compulsorily greater than k plus 1 whole cube by 3. That means P of k plus 1 is true. So means it is verified for n is equal to k plus 1 also. Therefore, as it is verified for n is equal to k plus n is equal to 1, no, n is equal to k, and at n is equal to k plus 1 means at these three steps it is following all the three steps. according to the principle of mathematical induction, we can conclude that this statement is true for all the values of n. So children, I hope you all have understood all the concepts involved in this chapter. Okay, I'm sure that you will be scoring compulsorily 7 marks out of 7. So therefore, you all can get out of your examination, and you can continue the further chapters. So children, just let me review what we learned in these two sessions, especially in today's session. What is that? We have applied the principle of mathematical induction to verify some of the mathematical statements are true or not. But that what is there? First, by considering the given statement as P of n, and we have verified that at 3 steps, that is by substituting n is equal to 1, and at the second step assume that it is true for n is equal to k, and also proving that it is true for n is equal to k plus 1, etc. By using the principle of mathematical induction, when it follows all the 3 steps, it will be true for any value of n. That itself is the main concept, one very simple and only concept of this chapter. So students, you follow and be regular. You try to attend all the sessions compulsorily and try to understand each and every concept and try to present in your examinations very well. Okay, children, I wish you all the best, and I thank all the officials and all the members who encouraged me, who supported me to take this session. Thank you, one and all. I'm very much pleasure to wish you all. Thank you very much. Thank you, one and all. Thank you.
Thank you, Rajprabhu sir.
Thank you, madam. Welcome, madam.
You have covered all the questions and problems related to mathematical induction.
Yes, madam.
Dear students, sir has covered all the variety of problems. In earlier class, the nth term was given in the question, in the statement itself. But now, for the today's problems, sir has found the nth term using the nth term formula which we have learnt in class 10 of progressions. Nth term of AP is A plus n minus 1 into D. Nth term of a geometric progression is A into R power n minus 1. These two formulae sir has used in order to identify and obtain the nth term of the given statements. Sir, could you please go back to the previous problem where you found nth term, sum to n terms of a geometric progression?
Yes, madam. 1 second, please.
Yeah. Students, it is as simple as this. The principle of mathematical induction is common for all the problems that we solve. The first step is n is equal to 1. Of course, we take LHS and RHS and prove if they are equal. We say it is true for n is equal to 1. Very simple step. Then we take n is equal to k and we assume the statement to be true. So what is that step that we need to do? Rewrite the entire given statement, replacing n with k. That's all. That is the second step. Are you able to follow, children? We have to write n is equal to k in the given statement and put it as the second step. That is induction hypothesis. Whenever it is true for n is equal to k, we have to prove as a third step that it is true for n is equal to k plus 1. Then only principle of mathematical induction is applicable. And with that, we can say that it is true for all natural numbers. Now, going to the next problem.
Next problem, madam.
Yeah. In all these problems, sir has found the nth term using the formula for nth term in arithmetic progression as well as nth term formula for nth term in geometric progression. See, children, some of you were asking that this problem to be repeated. As we are running out of time, I will quickly go through what is the nth term here not given, isn't it? Can you go for slideshow, sir? From the current slide? Mm-hmm. Yeah, when nth term is not given, we use this is geometric progression, A into AR, A plus AR square, isn't it? So in the first term r power 0, in the second term r power 1, in the third term r power 2, in the nth term 1 less than n, a into r power n minus 1. That sir has found out. Then he has substituted n is equal to 1. The statement is true for n is equal to 1. That's what we have to prove. What is LHS? A into r power 1 minus 1. R power 0 is a, nothing but the first term. What is the right hand side? R power 1 minus 1 by r minus 1. They get cancelled and you have a. Is it not? So it is true for n is equal to 1. There is no doubt. I'm sure there is no doubt. Probably you got it out in the third step. The second step is what? This is C. Such a detailed explanation is given. Substitute n is equal to 1, r minus 1 will get cancelled, a. When n is the second step is assume that it is true for n is equal to k. Right? Please stop, sir. So here the statement is written just by replacing n with k, nothing else. You see the bottom statement, a plus ar square, so on till ar to the power of k minus 1 is equal to a into r power k minus 1 by r minus 1. This is what is the statement replacing n with k. Now is the next term. What do we have to do? See, here only in the first step you can see the right hand side. A into r power, a of r power n minus 1. That means in the place of n, what do you need now? K plus 1. That's all. That is what we need. For that, what do we do? See, we have taken the nth term, kth term and k plus 1th term. When you replace n with k plus 1 minus 1 will get cancelled. And what is the term you have? A r power k. A into r power k is the next term. This is the common procedure we have been following. So sir has added the next term on both the sides of equation 1 and then simplified the right hand side. You please look at this, how sir has done in detail. Can we go to the next slide, sir? Yeah. See, when you add this, this is LCM, nothing but a into r power k minus 1. R minus 1 is the LCM. A into r power k of r minus 1. Just multiply a into r power k minus 1. Here also a is there. Sir has taken a common. R power k into r power k plus 1. R power k into minus 1 minus r power k. This is quite common. Now minus r power k plus r power k got cancelled. What is left? R to the power of k plus 1 minus 1 by r minus 1. Now you compare this with the right hand side. See, right hand side is there on the bottom, at the bottom. In the place of n, what do you have here? K plus 1. So LHS is equal to RHS and P of k plus 1 is true. Therefore, by principle of mathematical induction, as we have satisfied and proved that the 3 steps follow, then by principle of mathematical induction, it is true for all natural numbers n. And the condition is r should not be equal to 1, that sir has explained. I'm sure now, even if you have still doubts, you can revisit the session and clarify your doubts, children. You can, and until and unless you solve them practically, I don't think you will be able to have a hold on this topic. You solve all the questions given in the textbook so that you actually follow what is mathematical induction, what is the principle of mathematical induction and steps involved. Almost 8 to 10 problems sir has already explained in those 2 sessions, right? So that will be sufficient for you to do the practice. Thank you for a patient listening. Thank you, Prabhu sir, for a wonderful and very soothing explanation, detailed explanation. Thank you so much. Thank you, one and all. Dear children, you have an English class after this. Stay tuned. We will come back in a short while. Thank you.
Thank you very much for your wonderful cooperation. Thank you.